Hello, and welcome back to the third and final speedrun of the IB Math textbook today. And so we'll be going through tangents and normals and more on, differentiation. So let's jump right in. So the first thing we need to talk about is we need to talk about the relationship between differentiability and continuity. If a curve is differentiable at some point, it is also continuous at that point. But it's not the same the other way around. If a curve is continuous at a point, it doesn't mean it's differentiable. So take the absolute value function. At this point over here, the curve is certainly continuous, but it is clearly not differentiable. Since as you approach it from the two different sides, you'll get two different gradients. This gradient will tend to 1, this gradient will tend to -1, so it's not differentiable. But it is continuous. So that's the first thing. Now the second thing is we need to talk about tangents and normals. So earlier we talked about finding the gradient of the tangent line, but that's not all. To find the actual tangent line, we need to account for the constant, because in all linear lines that look like y equals mx plus c, we need to find this constant over here. And we do that by plugging the gradient of the tangent back into the original curve at that point and trying to find what the constant is. If a tangent line has a gradient m, then its normal, well, the normal is a line that's completely perpendicular to the curve at this point. And it looks like this. So it's perpendicular to the tangent, and the gradient, of course, will be -1 over m in this case. So yeah, knowing all of this, let's jump into some questions to see what we mean. I will be doing I don't know, which one should I do? I guess I'll just do the odd ones. Why not? So we get the function f of x equals 2x squared minus x plus 1. We want to find the gradient of the tangent to the curve at x plus 1. So tangent at x plus 1, at x equals 1. The equation of the tangent, so the gradient of the tangent at x plus 1, the equation of the tangent at x equals 1, and the equation of the normal to the curve at x equals 1. So normal at x equals 1. Okay. So to find this, we first need to differentiate this. So by first principles, limit as h tends to 0 of 2 times x plus h squared minus x plus h plus 1 minus 2x squared plus x minus 1 all over h. So this will be equal to, if we cancel out the 1s, and we already cancel out the 2x's and the x's, well, we'll get from this is 4xh plus 2h squared minus h all over h. And so, as this tends to 0, this entire thing will tend to 4x plus 2. No, 4x minus 1 actually. So, yeah, this is the derivative of this curve. So f prime is equal to 4x minus 1. Now, first we need to find the gradient of the curve of the tangent at x equals 1. So, well, we can simply substitute 1 into here, and so that's equal to 4 minus 1. It's equal to 3. So the gradient is 3, and we need to find the we need to find the line at this point. So we know that y is equal to 3x plus c, where c is a constant. And to find this equation of the tangent, we need to plug 1 back into the original equation and see what coordinates it pops out. So this would be 1 and then 2 minus 1 plus 1, which is 2. So the points 1, 2 must be on the line. So if the points 1, 2 are on the line, that means 2 is equal to 3 times 1 plus c. And so in other words, c must be equal to -1. So the equation of the tangent is y equals 3x minus 1. Okay, finally, we need to find the equation of the normal. So we know the gradient of the normal is equal to negative 1 over 3, or negative 1/3. And so we need to plug this back in. So y is equal to negative 1/3 x plus c. We know that the point 1, 2 must also be on this normal curve. So we have 2 is equal to negative 1/3 plus c. And so c must be equal to 7/3. And so we have y is equal to negative 1/3 x plus c as the normal. Now one last thing, this is one way to arrange a linear equation, but there are other ways, and sometimes how you would express it is in the form ay plus bx, ax plus by plus c equals 0. And that's how they're asking us to express it, so let's rearrange this. Sorry, negative 1/3 x plus 7/3. And so we have a times x. First of all, we want to multiply everything by 3, so we get 3y is equal to negative x plus 7. And so therefore we have x plus 3y minus 7 is equal to 0. So this is the equation of the normal. Okay, on to the final question, and the final question is find any points on the following curves that have horizontal tangents. The first curve being y is equal to 2x squared minus 1. To find points on this curve that have horizontal tangents, first we want to differentiate it. So 2 times x plus h squared minus 1 minus 2x squared plus 1 all over h. So this is equal to the limit as h tends to 0 of 4xh plus 2h squared over h, which is equal to 4x. So the gradient at any point on this curve will be equal to 4x, and we need to find points on this curve that are parallel with the x-axis. This will be parallel with the x-axis if the gradient of this curve is 0. So we need to set 0 is equal to 4x, and so therefore the point where x equals 0 will be parallel to the x-axis. So that's the answer for this. And on to the final question, which is y is equal to x cubed minus 1. So let's find points parallel to the x-axis for this. So this is the limit as h tends to 0 of x plus h cubed, minus x cubed, plus minus 1 here, minus x cubed plus 1 all over h. So this is equal to the limit as h tends to 0 of 3xh. This is cubed, right? So 3x squared h plus 3xh squared plus h cubed all over h. And so if we differentiate this, we should end up with we should simply end up with 3x squared. So this is the equation, and we need to find when this is equal to 0. And this is also pretty simple. It's also when x equals 0. So yeah, that was it for this speedrun. I hope you enjoyed it, and I hope to see you in the next speedrun. Bye bye.